Hi, welcome to this video. My name is Phil and I'm a senior lecturer in astrophysics at the University of Lincoln, and I want to use this video to kind of come back to the habitable zone, but this time around we're not going to look at a star that's on the main sequence, but a star kind of like the Sun that has come to the end of its life, so basically a white dwarf star. And we're going to see if they can have habitable zones and potentially can they have a habitable planet. Now before we do that, I'm going to recap what the habitable zone is. So if you've seen some of the other previous videos, then you can kind of skip this first section. But if not, then I'm going to kind of recap what it actually is anyway. So the habitable zone, this green kind of ring around the star with the planet in, with its orbit as well. And this is the distance from a star where there would be liquid water present on the planet. So it's kind of like you've got like a window essentially, you've got like a band, or it's got a width to it essentially, where it can be where you'd basically have liquid water, and that's known as the habitable zone. Now if you're too close to the star, you've got that red section there, it's going to be too hot. So that section there, too close to the star, you're not going to have liquid water on its surface, it's going to be too hot. It's not going to be habitable. And then on the outer section, it's going to be too cold. So therefore, the planet wouldn't be habitable either. So it's got to be kind of in between those two there. And luckily for us, Earth is in the habitable zone. And we found plenty of exoplanets in this particular zone around other stars as well. So the thing is, this habitable zone does change with the type of star that it is. So we've got the Sun at the top there, and you can see this kind of band, this kind of bluish band across there, and you can see Earth's kind of somewhat in the middle. You've got Venus and Mars towards the outer edges. Obviously Mercury and Jupiter are outside that. And then you've got this other star, which is a red dwarf star, and you've got the planets, you've got E, B, C, D, and C and D are kind of on the outer edges of being habitable, but notice how much closer they are. Red dwarf stars are much smaller, they give off a lot less energy, so the planets have to be closer to have the same level of energy that reach their surface and the same kind of warmth, I suppose, to have liquid water. So, red dwarf stars, as I just mentioned, your planets have got to be quite close actually, so very close to the actual star to be habitable, because they just don't kick out a lot of energy compared to a star like the Sun or a much bigger star. Much more massive stars are much hotter, and therefore your planets need to be much further away to then have a habitable surface, I suppose. To have liquid water on their surface, they've got to be much further away because those stars are, well, they have a much higher luminosity. There's a lot more energy coming from their surface, so the planets are going to be much further away. So it depends on the type of star that it is, where this habitable zone essentially sits. Now, we can calculate where that zone is going to be, and we basically need the luminosity of the star. Now this is the HR diagram. If you're not familiar with it, I've got some videos on that as well where you can kind of check that out. But the HR diagram is just a scatter plot of known stars against luminosity and surface temperature. It can also be like magnitude flux in exchange for luminosity, and it can also be, instead of surface temperature, it can be the spectral classification as well, which is a function of that anyway. So then we have this HR diagram. What we need is the luminosity of the star to calculate how far away a planet needs to be habitable. And it's typically given in luminosity units of the Sun. So if you see this symbol here, the L with the circle and the dot, that means it's a solar unit. And in watts, that's the luminosity of the Sun given there. I'm not going to say it, it's a very big number, but in astrophysics, astronomy, we typically use these sorts of units so they're easier to understand. So if I say a star it's got 2 luminosities of the Sun, we know it's twice as luminous. So it kind of makes a bit more sense than just having a massive number, really. So for example here, we've got a more massive star, it's more luminous, it's twice the luminosity. So we would write that like this here. So the L star is normally referring to the luminosity of the star, and that would be 2 times the luminosity of the Sun. So typical units are used like that, really. And as we go and calculate the habitable zone, we'll use those units as well. So we can then calculate the inner boundary where it becomes too hot, and we can use this fairly simple equation here where it's the luminosity of the star divided by 1.1 and then square rooted. What that will do is it will give you the inner radius of the habitable zone in astronomical units. That's what the AU is. Now, 1 astronomical unit is the average distance of the Earth to the Sun. So again, it all makes kind of sense. We can kind of gauge what that distance is instead of putting it in meters, kilometers, or other units, because they're just going to be massive numbers. We can do the same for the outer region. This time round, we're actually dividing by 0.53, and that's going to give us the outer edge of that habitable zone. So if we write the two equations here, we've got the inner and outer. That unit there, as I mentioned before, the L star is just the luminosity of the star in terms of the Sun. So if it's twice the luminosity of the Sun, we'd put a 2 there. And then we've got our astronomical units, as I just mentioned. That's the average distance between the Earth and the Sun, and that will give us a distance essentially in that, which again makes a lot more sense. So if we do it for a Sun-like star, so for the solar system essentially, we get the inner boundary being about 0.95 AU, and then the outer boundary is about 1.37 AU. So that gives us our kind of boundary where the habitable zone exists around a Sun-like star, for example, the solar system. If we do it for a star that's twice as luminosity of the Sun, or twice as luminous I should say, then we get these values here. So it's about 1.29 to 1.94 is our habitable zone. So it's moved further out. We kind of expected that because we know it's more luminous. The planets have to be much further away. So if we want to then do it for a white dwarf, we need to have its luminosity. So the luminosity is going to determine our habitable zone. Now on the HR diagram, these white dwarf stars sit quite low down luminosity wise. They're very small stars. Whilst they have very high surface temperatures, they're quite small. So they sit in this little group at the bottom there. So we still need this luminosity then to calculate our habitable zone for a white dwarf. So to put it in context, when I say they're small, they're typically the size of terrestrial planets. So Earth size, Mars size, depending on its mass. The more massive they get, they actually shrink due to the way they are. They don't have any outward radiative pressure. These are degenerate stars, so they're only held together by electron degeneracy. So that if you add more mass to them, they actually get smaller because they get more compact. But anyway, they're typically around about the size of a terrestrial planet, so very, very small. And the typical luminosity of one of these white dwarf stars can range from like 0.01 to 0.001 solar units basically. To be honest, there's quite a range there, and they're basically not very luminous. And it depends on its temperature and its size really. So its luminosity can be considerably lower than a normal main sequence star. So what we can then do is we can essentially calculate where these zones are going to be. So if we take kind of the upper limit then, it's about 0.01 times the luminosity of the Sun, we get a distance of about 0.09 AU to 0.14 AU. If we do that for a less luminous white dwarf star, then it starts to get very close indeed. So you're talking 0.009 AU and 0.014 AU. That's incredibly close to the star. And that, they're very small numbers, but in context to the Sun, it's actually going to be just outside the radius. So if we put a planet on one of those sorts of orbits that was in the habitable zone of a white dwarf, it would only just be outside the radius of the Sun. So it's very, very close to the star. But I suppose the good thing really with a white dwarf is they are considerably smaller. So it isn't going to be just outside the radius of a white dwarf star, but it is still going to be very close, just so it can get enough energy on the surface of that planet to be habitable basically. Now, I will leave you with this to think about. So whilst you can have a habitable zone, potentially habitable planets around a white dwarf, they're very close to the star, but you have to ask yourself, how did they get there? How did they survive? Now that's a planetary nebula, and that's an intermediate stage between a red giant and a white dwarf, which would be typical for a white dwarf star. And look at all that material. That can disrupt the orbits of planets, maybe even destroy planets, send them inwards, alter their orbits. So if there are planets in the habitable zone around a white dwarf, how did it get there? maybe it was captured later on, it came along after the white dwarf formed, or it somehow survived, but it's had to go through a fairly harsh environment that the star was kicking out to survive. So if it was habitable, it probably wasn't after this process. So it's worth thinking about, really, if they are there, how do they get there? How do they survive? Are they still habitable? So thank you for watching. If you enjoy the videos, then consider becoming a member. There's extra videos in the member section, but it also generally helps support the channel. So thank you for watching.